Okay, this is part two of the Intro to the Solar System unit review. Part one covers from the beginning, which is overview of the solar system through meteorites and meteoroids. So this part will cover comets through solar system formation. So it's just a good little snapshot of comets and how weird they are astronomically as far as our solar system. So I like this picture because it shows how comets can go out thousands of AUs and have these crazy elliptical or in eccentric orbits and come into the sun randomly, or not into the sun, but um, into the inner solar system randomly. So some of their orbits are quite unpredictable because we haven't seen a lot of them before in recorded history. Comets have four major components that we identify in the class. The nucleus is the structure itself. So if you look right here, it's a ball of gas and dust kind of mixed together, and it's usually referred to as a dirty snowball just because it's mostly ice, but it has some dirt in it too. As the comet starts to approach the inner solar system and come in contact with the solar wind particles from the sun, the coma will start to be generated. And the coma is what's typically referred to as the head of the comet. And this is ionized gas that the sun is basically exciting because of these extra electrons that the sun is sending out. So after the coma is excited, a lot of that ionized gas will kind of trail off at an angle like so. And it's just referred to as the ion tail. It used to be called the comet's tail, but we've further studied it and realized that the ion tail and the dust tail are two different things. So this is the gas that's being released, and it kind of streaks away in a fairly thin little line. And the dust tail is whatever was caught in the ice just kind of trails away. Very important thing to note about comets is the tail always points away from the sun because the sun is generating pressure in the form of solar wind, so it kind of blows it away as if it was like wind. So looking at this diagram, you have the nucleus be the very center of this thing. B is pointing to the outer edge of this, so this would be the coma. C would be the dust tail, right? This stuff is being kind of let go as the gas is ionized, and this is the ion tail here. It's a lot sharper and more defined, whereas the dust tail is a little more diffuse. This is my review of what an ion is. If you remember from chemistry, sodium and chlorine will ionically bond, but an ion is a positively or negatively charged atom, right? So in this case, you have things that are being charged due to interactions with electrons from the sun in the form of the solar wind. So as a comet comes into the inner solar system, the ion tail will form first. And as it gets closer and closer, more gas is being ionized, and what happens is the dust and dirt and debris or whatever is released from this chunk of ice, aka the dirty snowball, forming the dust tail. Two major regions that comets live in. Now, some comets do live in the asteroid belt, but most of the comets in our solar system live in these two regions. The short-range comets are referred to as Kuiper belt comets or Kuiper belt objects. Now, this is 30 to 100 AUs, right? This is short is a relative term, right? Obviously, that is a long ways away, but in terms of a comet, that is shorter. Longer range comets are 100 plus AUs, right? So this is a region we know as the Oort cloud. And if you look at this, I like this diagram because this shows the entire inner solar system right here. And these short range comets kind of make a belt that's fairly flat along the ecliptic, and we call this the Kuiper belt. It's much like the asteroid belt, but it's comets. And it's much closer, relatively speaking, to the solar system than the Oort cloud. So in this image over here, you can see the Oort cloud is this giant sphere of just kind of random, crazy comets. And they call it the cloud. This looks similar to the electron cloud theory. But in this picture, you can actually see this image right here, which is going all the way out to the Kuiper Belt, is entirely within this box. So this really goes a long ways out. And if you look at this scale down here, the 50,000 AUs, that really helps to understand how far away the Oort cloud is. So the Kuiper Belt region has what we call icy planetesimals, right, which is essentially the same thing as a comet, right? It is a lot of ice and some dirt. Some of these Kuiper Belt objects, we believe, do not actually come in the inner solar system, but are just kind of staying out there. I believe they're gravity assisted into the outer solar system, probably by Neptune and Uranus during their early solar system formation, just kind of flung out there gravitationally and never, regained enough gravitational energy to come back into the inner solar system. A lot of them were in the inner solar system during the formation of the entire thing, or the entire solar system, but these were accreted to terrestrial planets. This is one of the main theories of how Earth got water. So the Earth and every other terrestrial planet has been bombarded, gazillions of times with comets. And asteroids, for that matter. Probably the most famous comet is Halley's Comet. It has an orbital period of 76 years. It was first predicted by Edmund Halley, who's a British astronomer, and he predicted the orbit based off of data that he had used, and went all the way back to the Chinese data and calculated it several different times and predicted that it was a roughly 76-year period, and he was correct. So it got named after him. He did not name it after himself. In the late 90s, or maybe mid-90s, I don't know, I can't remember, the comet Wield 2 was going around in Mars's orbit, and NASA decided that they would collect some of the dust-tail debris from it into a spacecraft mission known as Stardust. And they collected it with this stuff called air gel. And this is what a piece of air gel looks like, and it's 99% air and a small amount of silicon that makes it up. It's a weird substance. They put it in this grid-like section and kind of flew this tennis racket arm looking thing with air gel through the dust tail, and it brought back amazing samples, including the idea that it found the amino acid glycine, which is huge because comets have long been believed to be some of the life givers of planets, if you will. So Kuiper Belt objects are typically shortened or abbreviated to KBOs. So you'll hear astronomers talk about the KBOs and KBOs this and KBOs that, and that's what they are. So, like I said earlier, belt of comets, much like the asteroid belt, further out. This is just a slide that shows some of these other KBOs, and they're now being known as trans-Neptunian objects, which simply means it's, further than Neptune out. So these are small, relatively speaking. Pluto is one of the largest ones. Eris is believed to be larger now, but some other ones that we found. Not we, as in I've done it. Well, in 2006, the International Astronomical Union decided to reclassify Pluto as a minor planet because all these KBOs are starting to be found, and they decided they really need to classify what made a planet by these certain different criteria, and Pluto didn't fit it in certain criteria, so they decided to reclassify it. I believe it's a good classification. Now, in 2015, the New Horizons spacecraft did a flyby of Pluto, and we got our first actual images of Pluto, which is amazing footage, and this is an actual image from the New Horizons probe. This is a false color image, just to kind of make some other details pop out, but it is a real picture. So I just showed some of the different images from Pluto and some of the different theories about, was it possibly a failed gas planet and stuff like this. And obviously, at the time of this video that I'm making it right now, right, this is October the 1st, 2015, and this is data that's literally not even 3 months old, so we're still very much figuring it out. So, and these are just additional images, which I really didn't talk about much in class. I just kind of was pointing to the new data that was coming back from New Horizons, which I just thought was interesting, and I thought the students would want to know. It's really not going to be anything tested about this. I just think it's cool. So the last thing we're talking about for this unit is the solar system formation. It's known as two different major theory names. Right? It really is typically known as the nebular theory. I hate to say that it's always known as two names. It's really the nebular theory, and it's the idea that it starts with a nebula, right? But it's oftentimes you'll see something mentioned about the condensation theory. So I put both of them on there. So the nebular theory is this giant ball of gas and dust that somehow starts spinning and contracting, and as it starts spinning, gravity starts to make things accrete together, which is basically collide and stick together due to gravity. As these things do this, conservation of angular momentum will make the whole cloud spin faster and faster. As this cloud spins faster and faster, it will start to flatten out, much like pizza dough that's thrown into the air and is, basically made into this large flat dough that we all think is delicious. So let's move on from that, and then we'll get into some more of the theory in a second. Obviously, some of this stuff's question marks as far as how big the cloud of interstellar debris is and how long it takes. But we believe it's roughly a light year in size, which is relatively a large body of gas, but it's nothing, crazy big. Mostly made of hydrogen and helium because that's what most of the universe is made of. However, it's not entirely hydrogen and helium. There's definitely some heavier elements like carbon and oxygen and uranium and things like this. And we know that because these elements are on Earth, right? So, these elements came from the insides of a heavier mass star that supernovaed. And we know that because some elements that are present on Earth are only created during supernovas. For instance, anything above atomic number 26, which we have lots of things on planet Earth above atomic number 26. But one that's typically looked at is uranium. And uranium is only made in, most certainly only made in supernovas. So things like that kind of reveal that there was a larger star here that exploded, and we are made from the leftovers of that. So accretion is what's known as the building up of mass by collisions, right? And it's just like one thing collides into another thing, and another thing collides into another thing. And I always say it's like a piece of dust collects into a dust bunny, and then a dust bunny collects into, a dust dog, and then a dust dog collects into a dust rhinoceros or whatever, right? So I'm just obviously joking about the animals, but they just get bigger and bigger and bigger. So who knows the time? Time is shaky. According to models, right, we do computer model simulations on this, in about 100,000 years, these small moon-like bodies that we call planetesimals start to form. And they're about 100 kilometers in size, which is really pretty small. I mean, it's bigger than your average asteroid, but it's not quite even a moon, really. So these things will start colliding into each other, and because they're larger, they have larger surface area, they're more likely to hit something else floating around in space. So they will continue to form with other matter and smash into each other, and then they form what we call protoplanets. And protoplanets are just larger bodies. They're not quite planets as we know them yet, but they're getting there. So if you look at this diagram, this really kind of shows the general idea. Planetesimal stage of solar system formation, there's probably thousands of planetesimals, if not 10,000. As time goes on, these things collide into each other. The solar system starts to thin out. And you can see here in all the orbits here, there's a gazillion, bajillion of them. But here, there's definitely less of them, right? Now, obviously, there's still some here, but here there's less of them. And as a result of that, these things, as they continue to smash into each other, they will mature. The solar system will mature or clear out, and it'll form what we see as a mature solar system, which is what we believe our solar system is currently. Now, a lot of the material gets cleared out by what's called, it's a stage of the sun or any star called the T-Tauri stage. And the T-Tauri stage is a point when nuclear fusion starts in a star, and the solar wind is extremely powerful, and it blows all the gases from the inner solar system away. And a lot of the things in the outer solar system are able to retain those gases because they are larger already, have more gravity, and they're further away from the sun. The actual image from 2014, BBC News took of a solar system forming. I love this picture because these little paths that are cleared out, these are where planets are going to form. So, like I was just saying, the Jovian planets, since they're further away from the sun, they started accreting matter in larger amounts earlier than the terrestrial planets because they weren't. Terrestrial planets are basically competing with the star a little more, but they start collecting mass at a quicker rate, and also don't lose as much mass from the T-Tauri stage or the extreme solar wind of the sun when it blows it out because they're so far away. So these are like norms we see in the solar system that we think are common in all solar systems, right? Planets are isolated. They're isolated because they've cleared out their orbital paths due to, accretion. Anything in their orbital path that stays in their orbital path eventually gets eaten by the planet. Orbits of planets are near circular. They're very stable. They all lie on the same plane, which is what we call the ecliptic. All the planets orbit the sun in the same direction. So this makes a lot of sense as to why the entire thing formed at the same time, right? The planets didn't form randomly sometime after the star, right? This is all forming at the same time from the same cloud that was spinning in the same direction. Planetary systems differentiated, which simply means there's different kinds of planets, right? We have terrestrial planets close in, and we have Jovian planets far out, right? We don't have a terrestrial planet in between Jupiter and Saturn, right? If that's the case, then we couldn't say that it's highly differentiated. We would just have to say, well, sometimes planets can just happen wherever they happen. No, we believe terrestrial planets tend to form close to the star, and then Jovian planets tend to form further out. Kuiper Belt's well-organized ring of leftover stuff, right? This is what we believe to be common in solar systems, but not just ours. Those are a few things that are a little bit weirdo in our solar system, and I'm sure every solar system has its own little irregularities. Mercury has a 3-2 spin orbit resonance, which simply means that it gets tidally locked when it's orbiting the sun, and that's because it's so close to the sun, right? Other planets don't really get tidally locked from the sun. Venus has a runaway greenhouse effect. We think that's bizarre. We're not sure that that's bizarre. That could be a norm in another solar system. In fact, it probably is. Who knows? We know that Earth has life. Is Earth the only planet with life, right? Why does Mars not have life? So these are things that are unique to our solar system. At least at this moment, we believe that. We do believe that, Earth is not the only planet that has life on it. Most people believe that, obviously. There's no scientific proof, but most people tend to believe that Earth is not the only planet with life on it. But right now we don't know, so we have to assume that is a unique characteristic of Earth at the moment. So, all right, well, that's pretty much the end of part 2 of the unit review. Hope that you guys are getting ready for the old tests, and I'll see you at some point in class.